Okay, so I think we'll get started. So welcome everyone to the ARMET seasonal forecast outlook for the energy sector for this winter. Um, Good to have you all here. You've got three great talks for you lined up this afternoon. We've got a seasonal forecast, and we've got two speakers who will be discussing how the forecast and how winter weather impacts their outlook on the energy sector and the work that they do. Just a quick introduction for myself. I'm James Mollard. I'm the Energy Engagement Fellow with the Royal Meteorological Society. I'm chairing the session, so I'll just give you a quick introduction and then we'll get on with our first speaker. For those of you who haven't used Zoom before or who are unfamiliar with this, we have essentially the three talks and then we'll have a Q&A session. You'll see that for those of you that joined, there is a button with a Q&A box. If you have any questions during the talks, please put them in there. Other people will be able to see them and they'll be able to vote on whether, on your question, and those with the most votes will be the ones put to the top. After we've had the presentations, that Q&A session, we will then be able to put those questions to the speakers. Any questions that you want, you can put them in there throughout, rather than having questions during or after each presentation. If you're having any problems with the sort of technical side, there is a thing with Zoom in which the chat can sometimes take up the whole screen. If you're struggling to see the sides, please feel free to make the chat go away by closing it in the top corner. And if you are having technical issues, if you're not on the Zoom app or the Zoom program itself, we recommend that you use either Chrome, Firefox, Safari or Edge, and you can do that through a browser. You don't need to necessarily have the Zoom program installed on your computer to be able to access this. A couple of things just from the sort of ARMET side. If you are not already and you're an enthusiast of all things weather and climate, we invite you to sign up to the Met Matters newsletter. So this is a monthly newsletter that's put out by the Royal Meteorological Society every month. It has various different things on each month. We have all the information about our meetings, about our events in local areas. We have guest blogs, various stories, timely kind of reminders of what might be happening weather-wise throughout the year, as well as competitions and opportunities for your participation in citizen science projects. If that's something that's interested to you and you're not already signed up, if you go to armets.org/metmatters, you'll be able to sign up to that, hopefully after this event, not during. We hope that you stay here for it. And then if you aren't already, if you want to become a member of the Royal Meteorological Society, we are the leading independent experts in weather and climate as a society. There are lots of benefits to becoming a member. You become part of a community of over 3,000 other people who are like-mindedly interested in weather and climate. We have training, we have classes, we have certification if you work within the weather and climate industries. We have access to journals and publications with peer review publications as well. There's a mentoring scheme. We host lots of events similar to this in some cases. We also have events at local centres around the UK and other large nationwide events as well. And it also helps if you join to support our mission to advance the understanding of weather and climate and the education, and that's obviously to the benefit of everyone. If you'd like to sign up or you want to know more information, www.armets.org.uk, and all the information you'll need will be on there. So without further ado, I'm going to introduce our first speaker today. So we have Hazel Thornton from the Met Office. She's part and the manager of the monthly Decadal Prediction and Impact team there. And her research focuses predominantly on the North Atlantic and European climate variability, but also the impact of climate extremes on various sectors. and she's going to today share with us the Met Office seasonal forecast for the winter ahead. So Hazel, over to you.
Thanks, James, and thanks for the invitation from the Royal Met Office to come and present the Met Office forecast. I will just share my slides. James, could you just confirm you can see my slides?
I can indeed, yeah.
Perfect. So thanks, everyone. As James said, I'm Hazel Thornton. I work at the Met Office down in Exeter and in the monthly to decadal prediction team. So we're the team that produces the monthly, seasonal and decadal predictions. So thanks to the wider team for their input into this forecast. So just be aware, this forecast is a seasonal mean. So that means a 3-month mean for December, January and February. So it's a 3-month average climate forecast, and it was produced at the end of November. So a few of the slides might be slightly out of date because we're 10 days into December, so some of the things do evolve, but I'll mention those if they do. But just, yeah, this is the forecast for December, January and February. And the main question we're trying to really answer is, what will the winter on average look like? So if we think back to 2 contrasting seasons, winters, we had that of December 10, 11, and then December 2015 and the winter of 2015, 2016, where we had very cold conditions in 2010. So cold, calm, and dry conditions, whilst in 2015, here we can see some of the media coverage. So obviously, I've been lots of flooding, so it was a warm, wetter, windy winter. So we're trying to, can we forecast? What we're aiming to do is try and forecast the general type of winter that we're going to have. So today, I'm going to summarise the dynamical drivers of UK winter climate. Then what are the forecasts of those drivers currently? And then what does that mean for the December, January, February forecast? So just be aware, this is, the 3-month average conditions. So we're not trying to pick out, for example, a particular storm on a particular date or a 5-day cold snap, but rather on average, what are the conditions? And these are based on observations. They're based on coupled ocean atmosphere models from both the Met Office, but also from different modelling centres around the world, and some expert judgment. Okay, so on to the dynamical drivers of UK winter climate. So hopefully you're all aware of something called the North Atlantic Oscillation. And basically, this is a pressure difference, surface pressure difference between Iceland, where climatologically wise, we have low pressure, and the Azores, where we have high pressure. And so this difference in pressure leads to is what the index of the North Atlantic Oscillation is. So it can either be positive when the low pressure is low and the high pressure is high, we get a positive. So here we have a time series of this index. So positive values are for individual years have a red bar, and negative values have a blue bar. So this was this very cold winter of 2009, 10 and 10, 11. And why do we care about this North Atlantic Oscillation? Basically, because it dictates a lot about our UK winter climate, and this is the main driver of our UK winter climate. So when this pressure gradient is strong, so we're in the positive phase of this oscillation, we have an active storm track, so we have more storms, we have more winds from the west, and it's milder and wetter, and less frequency of snow. Whilst in the negative phase, when this low pressure is weaker and the high pressure is weaker, then the storm, the pressure gradient is not as strong, and we have a weaker storm track, often allowing for high pressures to develop. So where we have typically colder and drier conditions and calmer conditions. And so what we're trying to do is basically forecast the phase of this North Atlantic Oscillation. And the Met Office seasonal forecasting system, which is called GLOSSY, and it's version 6 at the moment, has skill in predicting this North Atlantic Oscillation. It doesn't always, it's a probabilistic forecast, and it's not always shifted the right direction. But over the hindcast period, we do have statistically significant skill, and that's true for some other systems as well. Okay, so what dictates the North Atlantic Oscillation? So this is just a picture of the North Atlantic Oscillation with that climatological low pressure over Iceland and the high pressure over the Azores. And there are basically a number of different drivers that can influence the North Atlantic Oscillation. And if they're all pointing in the same direction, then that anomaly might be very strong, whilst if they're pointing in different directions, then you might get a bit more of a mixed picture and not a particularly strong signal. So what are the things that matter? So this is a picture of sea surface temperatures across the globe, and this is in the Pacific. So here we have a La Nina. So these are your sea surface temperatures, blue being colder sea surface temperatures. So the El Nino oscillation can affect the North Atlantic Oscillation. Where we are in the sunspot cycle. Then we have the Madden-Julian oscillation, which is really more critical on the monthly timescale. But it can influence the stratospheric polar vortex and then have those influences further ahead. And then we've got the influence of volcanic eruptions, or something called the quasi-biennial oscillation, which is an oscillation of winds in the stratosphere, tropical stratosphere, and then what's going on with the polar stratospheric vortex. And is it particularly strong or is it weak? And all these things have influenced this North Atlantic Oscillation. So basically, in our modelling system, we want to be able to model all these different drivers and their influence and see, and that's how you produce a forecast. So what's the combined influence of all those different drivers? Okay, so what are the forecasts of those drivers at the moment? So we'll start with the El Nino Southern Oscillation, or ENSO for short. So this is a global sea surface temperature anomaly plot where blues are cold temperatures, sea surface temperatures, and reds are warmer temperatures. And we can basically see in the Pacific, the East Pacific, we are cooler than normal. And this is basically indicative of a La Nina. It's a weak La Nina at the moment. And then these are the forecasts from both the Met Office in the middle and the multi-model ensemble. So for different modelling centres on the right-hand side. And basically, this is where we are at the moment at the beginning of December, and the forecast. So negative values are indicative of a La Nina, and we are weakening. So we have a weak La Nina, and that is weakening further over the winter. So that's the Met Office forecast. And then this is the forecast on the right from the multi-model. And again, from November, you can see it's weakening further. So this is your zero line. So basically, we have a weak La Nina, and it's forecast to become neutral over the winter period. So what would a La Nina typically mean for our UK winter climate? So these show the mean sea level pressure anomaly plots for early winter, so November, December, and late winter, January, February. So in early winter, reds being higher than average pressure. So we have higher pressure. So the UK is just under my cursor there. That's Greenland. And we have higher than average pressure to the west of the UK. And so this typically would give you cooler, drier, calmer conditions. Whilst in late winter, it's actually the opposite. We have a positive NEO pattern where we have lower than average pressures over Iceland, which is under my cursor now, and higher than average pressures over the Azores. So you have a strengthened pressure gradient. So you have this positive NEO pattern in late winter. So this would typically, in January and February, a La Nina would typically give you warm, wetter, windier late winters. But it's not every year. It depends what the other drivers are doing and when they're constructively interfering or destructively interfering. So onto this QBO, the quasi-biennial oscillation. So as the title suggests, it's a nearly 2-year cycle. And where this happens to be, the way we typically measure it is the zonal winds over Singapore, but basically it's a representation of the tropical stratospheric winds. So this is pressure, so 300 hectopascals up to 10 hectopascals. So this is sort of in the stratosphere. 100 hectopascals is approximately the tropopause. And this is a time series, so from 1992 all the way through to where we are today. And basically, we can see that the winds reverse every couple of years or so from westerly to an easterly wind anomaly, westerly, easterly, westerly, easterly. And these descend through time, and basically they can influence the polar stratospheric vortex. I'll talk about that in a minute. But where we are at the moment is we are in this blue phase, which is an easterly phase. And what would an easterly phase typically mean? So this is a plot of the temperature difference from easterly minus the westerly phase. So basically you have colder temperatures in northwestern Europe and Asia during an easterly QBO. So what is the forecast for the QBO? So this is what's actually happened up to the dashed line here, and then this is the forecast. So we can see we have a descending easterly phase, and the height that we really care about is the sort of 20 to 30 hectopascals. So we consider we're in an easterly phase at the moment, and the forecast is for that easterly phase to continue to affect the winter. But you can see the next westerly phase is starting to descend. And what does that mean? So being in an easterly phase means we have an increased chance of a weaker stratospheric polar vortex, particularly in December and January, and an increased chance of easterly winds over northwest Europe. So there's colder, calmer conditions. So that's in contrast to what the La Nina was giving us. But we've also got to be aware of sun stratospheric warmings. And when you are in an easterly phase, when you have a weak polar vortex, you're more likely to have a sun stratospheric warming. And what is a sun stratospheric warming? Basically, we're showing pictures of vorticity. Not quite sure which level, but basically what this represents is the polar vortex. So in at heights in the stratosphere, the winds move in an anti-clockwise direction with very cold temperatures over the pole. And what can happen is either that can get shifted off the pole or it can get broken in half. And this is what's termed as a sun stratospheric warming, SSW. And why do we care about this? Because actually it can influence, in 60% of cases, when we have one of these events, we then end up with colder temperatures in northwestern Europe and many parts of the northern hemisphere. So this is why we care about it, and that happens approximately 1 to 60 days after the sun stratospheric warming. So we typically think sort of 2 weeks to a month after the event, you could get such cold temperatures. So we think from the beast from the east, and these are some of the classic sun stratospheric warmings and the influences, but not as we've just had a minor sun stratospheric warming. So it didn't quite reach we didn't actually get a reversal of the winds at 10 hectopascals, and it didn't influence the surface. So it doesn't always happen. It's only in 60% of cases that when you get one of these events, does it influence the surface. So what is currently happening? So as I said, this is a forecast from the end of November, and that was the point where we had this low wind speed. So we'd had this minor warming. And then the forecast, which is in the red here, was for a strengthening. So this shows you basically the strength of the polar vortex. It's called the zonal mean zonal wind at 60 hectopascals, at 60 degrees north, 10 hectopascals in height. But basically it's the strength of that polar vortex. And what we're showing in blue here is the climatological strength of that vortex. So it's strong over the winter, over December and January, then starts to weaken as you head towards the spring. So that's the blue. And here you can see the range, the quartile range, 25th and 75th quartiles. And then the red is the forecast. So the forecast was for, after that minor warming, to then strengthen, be a bit weaker, and then go back to the climatological strength. And here, this just shows, is a summary of those that cross this zero line. So this is the fraction of the ensemble members, which are each of these individual grey members. So the red, is the ensemble mean. And in each of these individual members represent the uncertainty in that forecast. And what we show here is the fraction of the members that actually warm, so across this zero, compared to the climatology, which is shown in blue. And basically, we can see we're very similar to the blue and the red lines are very similar, which basically means the risk of stratospheric warming from that point is the climatological risk. There's not really a strong signal. But these things can evolve rapidly. So it's very important to keep abreast, if you're particularly interested in cold weather, keep abreast of whether the stratosphere is active, and if there's a stratospheric warming, then it would definitely increase our chance of having cold and calm conditions. So just to summarize those teleconnections and drivers, so we currently have a borderline La Nina, and this would typically increase the westerly winds in late winter, so it would typically give a warmer, wetter, windier winter, whilst the QBO is in the easterly phase, and that gives the opposite, with a reduced likelihood of westerly winds. We're expecting the stratospheric polar vortex to be normal conditions at the moment, and also it's just to be aware of obviously the warming of UK climate and winters, and to be aware of that when you're thinking about the forecast, because we give the forecast relative to a climatology, which is the 1991 to 2020 period, and so naturally we're always starting have warmer and warmer winters relative to that period. So what do the actual coupled models give you? This is the Met Office forecast of December, January, February mean sea level pressure anomaly, where red is higher pressure than normal and blue is lower pressure than normal. This is for the Met Office on the left, for the European Weather Centre in the middle, the Korean Met Agency, who run a model, basically run the same model as the Met Office, but with different members, and the Météo France, so the French model. So just give you a flavour of the different outputs. So what does the Met Office show? So blue, we have lower pressure to the west of the UK. So we're basically, this is more of a positive NAO picture from the Met Office. ECMWF has weaker patterns with not really a clear steer on what the North Atlantic Oscillation would be doing. The Korean Met Agency is similar to the Met Office, but even stronger. So that definitely has a strong positive NAO forecast, whilst Météo France also has a positive NAO forecast, more similar to the, well, between the Met Office and the Korean picture. So basically 3 out of the 4 are going for a positive NAO winter, which is consistent with that La Nina picture. So just in words, there is an increased chance of lower than normal pressure over or to the west of the UK, with higher than normal pressure to the east, and that sort of represents, it's trying to summarise the spread of the different results. This may lead to slowly evolving weather patterns and increasing the chances of westerly or southwesterly winds through the season. Okay, so what's the actual outlook for UK mean temperatures, wind speeds, and precipitation? On the left, we have the forecast for temperature. On right, for precipitation accumulation in millimetres. And on the right, sorry, in the middle, and on the right, we have the average wind speed, UK mean wind speed. And what we show is basically the climatological distribution of UK mean temperatures is shown by the dashed line here. And what we have is the likelihood, so the higher up this axis we are, the more likely it is. And we have 3 categories. We have near average, which is the central 60% of the distribution. Then we have a cold category, which is the lowest 20%, and a mild category, which is the warmest 20%. So this is your climatological distribution. And then our forecast is shown in grey. And so you can see there's a bit of a shift away from the colder scenarios, and a bit of a shift towards the milder scenarios. But we do still have some ensemble members. So, and our forecast is made using lots of different ensemble members. So different runs of the model with slightly different starting conditions. And we do still have some which forecast very cold conditions and some which forecast warm conditions. And the shift of the distribution is to the right, so to milder conditions. So likelihood leans towards a mild season. It's the same for the precipitation in terms of the format of the figure. And actually here, it's really pretty similar between the wet, near average, and dry compared to climatology. So basically, it's a climatological forecast. And for the winds, it's also pretty climatological, with a slight shift away from our high wind scenarios but basically pretty similar. For example, for the calm tail, it looks pretty similar. So it's not the most exciting forecast, it has to be said, and I think this reflects the fact that the drivers are doing different things. So we have a La Nina, which is encouraging this mild, wet and windy forecast, whilst the QBO is pointing the other direction. So when the drivers don't really line up, then you're going to get something in the middle, which is your more typical climate. And then what we've got here is just put this forecast into context. What you'll have at the end of February, we can then go and do the average for each of these seasons, so December, January, February, and see where on this plot, where on the x-axis does the temperature actually lie. And what this shows is the results from previous years. So the last decade, so for example, 24-25 was last winter, and each of the three, the top is the temperature forecast, the middle is the precipitation, the bottom is the wind speed forecast, and all of them fell in the near average category. So that means the observation was somewhere, for example, in the wind speeds was somewhere between here and here for the precip, etc. Interesting things we can see over the last decade, we both had windy seasons and calm seasons, we've had wet seasons and dry seasons, but we haven't had a cold season. And that reflects the fact this is your general climate warming with anthropogenic emissions, and the fact that we haven't actually had in the last 10 years a cold season. If we went back further, we would have one. So, for example, 9-10 would be there, but not in the last 10 years. So it's now more typical that we'll be forecasting the near average or the mild. Anyway, just it's again the forecast, but in numbers this time. So in terms of temperature, there's a 10% chance of cold, a 65% chance of near average, and a 25% chance of mild. And so this is this slight increase. Climatologically, we'd expect 20%, so it's a slight increase. So it's 1.3 times the normal chance. So increased chance of mild, reduced chance of cold. For precipitation, it is exactly as climatology, so it's exactly the normal chances. And for wind speed, again, it's pretty similar. For calm, the likelihood is the same as normal, or climatological likelihood. And there's a slight increase in the near average category and a slight move away from the windy, but it's still 50% chance of a windy season. So basically a climatological forecast in many senses. So just in words, finally, there's a greater than normal chance for the season as a whole to be mild. However, spells of cold weather and cold weather impacts could occur at times during the winter. So obviously that makes sense. We're doing a 3-month mean here, but you can obviously have shorter periods in that are different to the 3-month mean. The chances of a wet or dry season overall are around normal, with the chance of impacts from heavy rain or flooding similar to normal. And the chance of winter being windy overall is similar to normal. This does not rule out the chances of stormy spells, as we're having currently, or the impacts from strong winds at times. Okay, so thank you. That is the summary of the forecast. Just to say, we produce these forecasts every month. And over the winter period, we give energy sector briefings, which everybody is invited to. If you want to know more, go and see Rebecca Green. But basically, the next forecast for January, February, March is on the 23rd of December. So it'll be online. And then we have a briefing at the end of January for February, March, April period. So please keep updated. And here I've just put some links of the seasonal forecast and the month ahead forecast, if you want to know what's happening in the nearer term. Thanks very much.
Brilliant. Thank you very much indeed, Hazel. Very comprehensive there, and yeah, looks good for normal weather, whatever normal may be. I'll introduce our next speaker. So we've heard the weather. We're now kind of moving on to those in the energy sectors and the work that they're doing. So our next speaker is Lewis Morgan. He's the Policy and Resilience Manager at the National Grid Electricity Transmission. He works in their control centre there, and he works to deliver their transmission control centre protocols, but also looks at the impacts and guidelines for, in particular, high impact and low probability events. So if you have questions for Hazel or you have questions for Lewis and Desan, please put them up in the Q&A button just at the bottom of your screens. But for now, Lewis, take it away.
Okay. Thank you, James. I'll just share my screen. Oh, James, I think it's just stopping me from sharing whilst...
Hazel, are you still sharing? Sorry. There you go. You should be able to now.
Yeah. If you could just confirm you can see that there, James?
Yeah, that's perfect.
Brilliant. So yeah, so thanks, James. So this will take around 15 minutes. And yeah, as James mentioned, I work for National Grid Electricity Transmission, which is kind of what we define as the transmission arm of our business. So just to give some context to that, we're kind of like the motorways, if you like, of the power system. So large metal lattice pylons and substations, and then we transfer that power onto our lower voltage networks, which are operated by what we call distribution network operators, and that's where you would see more kind of wooden pole mounted equipment. So for the purpose of today, I'll be focusing on what we call electricity transmission. So just to give you a bit of context, we own and operate around 300 substations across England and Wales. And those substations are then obviously connected by a series of overhead lines and cables. Predominantly, it's steel lattice towers that we use to transmit between substations. So I guess the purpose of my talk today really is to give a bit of a feel, very much from an operational standpoint, of how we use weather forecasts and what actions we take in kind of operational timescales to try to respond to that. So to give a bit of context early on, we work to an incident response protocol, and that's what we call a bronze, silver, gold, or operational, tactical, and strategic response. And one of our greatest triggers, really, of our response is forecast extreme weather. And I've tried to put that into three kind of buckets. So we have a long-term forecast, and that's really what we use in terms of what we call prevention. So what would we do with that data? We would look at our network in terms of how it's meshed together, and we would make a decision in well ahead of time as to what risk we think is reasonable based on what the upcoming forecast is. We may also look at asset interventions, so physical changes or replacements to specific types of assets out in the field, depending on what the climate risk is that we're facing. But really, the short-term and the real-time forecast is where we're very heavily involved. So in terms of short-term, we'd be looking at how temperatures, for example, would affect the loading on our network. So that's the actual the power that people are using and how that affects our system. In the kind of 0 to 5 day window, whether we need to take any action to emergency return equipment that we've currently got switched out for maintenance, and also if we need to deploy any of our emergency equipment. So that could be temporary flood barriers, mobile compressors, or mobile diesel generators. And then really we move into what we call real time. So this is control center operations. And in that time period, we're very much focused on the safety of plant and personnel. So things like lightning and how that would affect the safety of our personnel. Emergency protocols, so determining whether we can restore supply based on what we think has happened to the network, and trying to understand what may have caused faults on our network, and kind of cross-examining that with what the weather forecast is telling us. So I've pulled out a couple of scenarios really to try and bring it to life. So one is storm events. So one of our biggest threats to our network is wind and lightning, which probably comes as no surprise. So Storm Kieran, which we experienced end of 2023, was actually quite a considerable impact on our network. Although the distribution networks have had bigger impacts from other storms, this was one that actually had a relatively significant effect to us, although we still maintained no loss of supply during that event. But what do we see? So predominantly wind speed on overhead lines and conductors clashing essentially. So we know areas where we've got exposed overhead lines with a particular vulnerability to high wind. And the same with lightning. So lightning can strike our kind of overhead lines, our towers, and that can cause a temporary disconnection of that line. And we have kind of automated systems. We term them delayed auto reclose. And those systems essentially will automatically disconnect the line and attempt to restore that line 30 seconds later once the effect of that lightning strike has passed. So we know these are critical systems in kind of keeping our supply on. So what do we feel? Well, during Storm Kieran, we had over 3,600 alarms received by our transmission control centre. So all those alarms need to be appraised and the impact of that determined. We stand up what we call a bronze command. So these are operational teams across the country located in the areas where we see the forecasters being specific. So we may look at moving resource around or bringing in additional spares from other parts of the country. We feel the effects ourselves, so our sites need power to function. We take that power from the lower voltage networks, and if there are failures on their networks, then that has an effect on us. So these are all kind of a real feel of what we experienced during Storm Kieran. So the other point I was just going to touch on was temperatures. So how does extreme temperature affect our network? So high and low temperature both really are significant, and also the rate of change of temperature. So our assets are insulated with things like oil, with SF6 gas, and those really are subject to, much like your car, during cold temperatures, the oil levels will drop, and we would start to receive low oil or low gas alarms on those equipment. So it's really important for us to be aware of where we are in terms of temperature and the kind of winter health checks that we would carry out on our assets. We also have a lot of mechanical systems, so compressors, pumps, motors, and as you can expect, cold weather has an effect on them and the ability for us to operate them remotely. But it can also help us. So overhead lines have a limited capacity, and predominantly that limited capacity is driven by the thermal inertia of the conductor. So during cold temperatures, that offsets the temperature from the current flow, and essentially it means we can give a dynamic rating. So it allows us to put more power through the lines when it's colder or windier. And obviously when it's hotter, we have to reduce that. So using weather forecasts and real-time weather data, we can try to maximize the power transfer across our network. And the third scenario that I've put in here is precipitation. And really this is flood risk. So as you saw at the start, we've over 300 substations and a considerably more amount of overhead line towers. And some of those are located in areas of flood risk. So that could be surface water, river flooding, or even tidal flood risks. So there's a range of actions that we take kind of in long term, and also in real-time timescales to try and mitigate that. So what you see on the right here is actually our live flood risk application. This was a screen grab I took today. And this is kind of environmental warnings, flood forecast centre, and Met Office data of where we see flood risk to our network and our assets. And that allows us to deploy personnel to sites where we think that we need to take action. In the long term, we deploy permanent flood defence systems to these sites, and we also have a demountable flood barrier system that we can deploy within sort of 2 to 3 days of notice. And I guess, what does that look like? So this was one of our substations, Walham, up near Gloucestershire, with flood defences in place, fortunately. But not all of our sites are fully protected to what we call ENA 138, which is an engineering standard for flood defence systems. We expect by the end of next year we'll have complete defence of all of our substations at risk. But there are other actions we can take. So I spoke about the demountable flood barrier system. We can also look to reconfigure our network remotely from our control centre, and also engagement with the local resilience forums, so emergency services and other responders under the Civil Contingencies Act that can support us where we see these kind of events. And my last slide, really. So as National Grid Transmission, as an organisation, we're kind of looking to develop both our business as usual kind of mitigations to climate-related risks, but also in an innovation front. So we are investing heavily in kind of trying to increase our knowledge of how various climate impacts will affect our network. And we publish a climate change adaptation strategy, which is available online. So you can go in there and see some of the work that we're undertaking. But that's all from me. So thanks, James.
Nice. Thank you very much indeed, Lewis. Again, if you've got any questions for Lewis, we have a Q&A session after our next speaker, and Lewis, along with Hazel and Desan, will be there to answer any questions you've got. So feel free. I see some people are already using that, the Q&A button. So please do continue to do so. So our final speaker this afternoon is Dr. Desan Kirley. She's a lecturer at the University of Edinburgh, a sustainable energy engineer and researcher. She's also the Elizabeth Georgeson Fellow in Data and Digitalisation for Net Zero Research. And most of her work looks at sort of using digital smart grid solutions to provide flexibility and resilience for energy grids. So Desan, if you'd like to take it away.
Perfect. Can you confirm that you can see the full presenter, not the presenter, the full screen?
Yeah,
on my presentation?
That's perfect.
Lovely. Perfect. Hi, everyone. First of all, thank you to James for inviting me to present our work on energy systems in the ARMED's talk today on seasonal forecast outlook for the energy sector. So today I'll be talking a little bit about how are we working on making our energy systems more responsive and resilient. Perfect. So energy systems is facing kind of a two-headed challenge. First of all, as we've talked today, there has been more frequent and also worsened and intense weather coming our way in different ways, which means that it's a new type of threat to the power grid resilience. We know of storms such as Dudley, Eunice, and Franklin in 2022 that left over 1 million homes without electricity. The second challenge is that we have higher energy demand. So you might be aware of incentives to have electric vehicles or heat pumps, or you might be owners yourself. While this is all great for decarbonizing our energy systems, at the same time, it means we have a higher demand. So more EVs actually also poses a different type of threat to the existing electricity infrastructure. The premise here is that if we could coordinate them effectively, then we could actually use electric vehicles as a means of distributed resilience. But this requires a lot of work in the background to make this happen. Following this, the motivation to kind of couple energy systems and response and resilience comes from this. We had a look at these two maps, and on the left, you can see from UKCRI, the climate risk plotting, where we have it higher in some areas. And then the other map on the right is showing the EV infrastructure in the UK as number of chargers installed per 100,000 people. You'll realize that in some areas, we already have a really good EV infrastructure, but we also have a high climate risk. So the idea was to use these existing EV installments and ownership to try and see if we could counteract the climate risk identified. So there is already an apparent need for coordinating all these new distributed assets in our energy systems, but how could we do that in a weather-informed way to increase awareness about distributed resilience in decision-making? As a side note here, I also want to say that the UK government Ofgem are currently looking to identify what should be the priority actions for enabling vehicle to X. So if you're not aware of this concept, is what other value we could get out of our electric vehicles. So one could be providing distributed resilience during extreme weather. On this project, we specifically looked at Orkney, and if I go back a slide, actually, you'll realize the Orkney Islands here in the north are both identified as high climate risk, and also they have a really good EV charging infrastructure. This might be a surprise to some of you, but Orkney Islands have been used as a test bed for different innovation projects, so they actually make a good case study for going forward as well. So what we've done is we went back and we looked at selected historic storm events that you can see here that have affected Orkney, and tried to see how we could have reacted to these differently if we had control of the EVs, and could we have made the power quality better? Could we have managed to keep the lights and the heating on? And if we're able to prove that as a feasibility study, how could we make this happen in real life on the way forward? So here what I want to show you is the changes we have in energy output when we have just business as usual or normal weather, as James said, whatever that may be. But also how the wind energy output is affected when we have storms and high winds. So what I want to draw your attention to here, so you'll see different wind turbines on the left and different hours at the bottom here is the 24-hour output, is we have 0 megawatt power output from different wind turbines. The reason why this is happening is because wind turbines have a cutoff wind speed. So they will be turned down if the wind speed is over a certain limit. So actually, even though we have so much wind to harness during high winds of a storm, we would need to turn them down, resulting in perhaps energy scarcity. So these events are resulting in a decrease in local energy supply, but at the same time, we might have a higher demand due to higher heating needs from energy users, but also EV charging as well if it is uncontrolled. So that's essentially increasing the problem we have, maybe tripling it. So it would also result in a higher stress on the grid, and it also indicates that we would need to work harder to do the balancing between energy supply and energy demand. So now we know we might have higher demand, but also the high winds are also resulting in a decrease in energy supply. So we have a mismatch between supply and demand, which often puts, Lewis also mentioned this, but the network operators kind of puts them in a really tough situation. And in extreme cases, weather can also end up resulting in network faults. So on the DRES project that I'll explain in a bit, we also looked at what kind of network faults have already occurred. Looking at the SSEN's database on faults, we identified quite a few different reasons why there might be faults. And the one that was prevailing was wind and gale. And we specifically plotted this for northern Scotland. And you can see in the Orkney Islands, we also have some peaks in places. So we focused on those areas that have the highest level of weather-related network faults. To be able to undertake this study, we needed data from a lot of different sources and different types of time series. And in some cases, we also had to use synthetic data because this proved to be a challenge. To summarize what kind of data goes into this work, we had wind generation, high voltage and low voltage loads, the fault registered, as I just presented, and also weather, and if it was available, some EV scheduling. So we have a code base associated with this if there is interest, and I have put some links at the end of the presentation if you would like to follow up and have a look. But in addition to the data sets I mentioned, we also mapped the EV charge points that exist in Orkney and also the network topology in Kirkwall in specific in the Orkney Islands to help us have a more localized and better informed study. So now I want to talk you through kind of our workflow and how we wanted to, what kind of services we wanted to contribute to. So one of them is a time of use tariff or frequency services, reserve and restore. You don't need to know what these are in specific, but these are essentially different ways we could use EVs to perform balancing and increase energy system resilience during extreme weather. Following this, we needed to do some kind of system state analysis, so understand whether it was just business as usual, normal weather, or whether we were on the horizon pre, during, or a post-climate event. Analyzing where we are and having that state estimation also determines what kind of services or what kind of response we design. And as the last layer, we essentially check whether the weather is normal or volatile, and what the EV availability is, whether it is low or high. And again, this affects the volume of the response we can provide. And all of this sits in a workflow with different kind of decision frameworks in between and is deployed on the Daphne platform. So DRES is kind of the decision mechanism, as I explained. This then connects with the network flow model to make sure that we don't violate any network operation limits and everything functions as normal needed. And on top of this, we do a bit of optimization to get the best out of the EV response as we can without causing any further problems to the grid. So what can we share so far? We have done this case study in the Orkney Islands in Scotland, but we're looking to expand to Southeast England and Wales. We specifically looked at passenger EVs and how to use them to provide different services to keep the lights and the heating on. We're also interested in grid scale batteries and other forms of energy flexibility. And as mentioned, because network faults were mostly affected by wind and gale, we focused on storm and high winds, but there is option to expand to other types of weather events if there is interest from you as well. So we built our modeling framework so that it can be taken by other people and expanded in different ways. And feel free to get in touch if you're interested in a special case study. I also wanted to touch upon the Daphne platform that I mentioned briefly. So as I said, I've put links, but if there is any interest in this, essentially what it does is it allows redeployment or reuse. So while we built this with the case study of Orkney, you might be able to use it, or you might want to adapt it and use it for different kinds of case studies yourselves, or we can also work on different case studies of interest to you. I wanted to talk a little bit more about different scenarios we simulated, and we have actually published this in a paper that, again, I have provided a link for further reading. We have different scenarios where we look at just basic EV usage, and then we perform smart charging, meaning we decide when the EV is charged within user limits, making sure that we don't override any of the user preferences, and again, don't cause any further problems to the grid. Scenario 3 does the same thing, but also vehicle to grid, meaning now we're using the batteries of the EVs as backup to provide energy reserve to the system. So you can think about it like a generator, almost pushing energy back onto the system when we have that decrease from the wind turbines due to high winds. So we've done this for normal weather and essentially repeated everything for extreme weather in the same order and compared different results. And if you're curious about what goes into it, we have EV driving patterns, generate different types of generators on the system, and also weather going in. And the outputs are an optimized EV schedule, also network-related outputs and key performance indicators, some economic analysis and CO2 analysis as well. So on a high-level note, we managed to show both economic savings, carbon savings, and also operation that does not violate any of the grid limits. So if we weren't to do this, we've also shown that there might have been damage to household appliances, would result in the long term in higher electricity bills, might cause disruption in industrial processes, more frequent power outages, and risks to hospitals, data centers, and other critical facilities. So this is why it's very important to design responsive and resilient energy systems going forward. And here's a plot that visually just shows you that essentially the area here, levels of low voltage, that comes from uncontrolled EV usage. But if we were to control it, we managed to mitigate the values within this circle, which is low voltage, pushing it higher into that, into the region that we would like to have for a healthy operation. Push it closer to 1 essentially, and allow a healthier operation of the grid. So quick thanks and acknowledgements. I wanted to specifically thank the team on the DRES project. I closely collaborated with Dr. Lai Suto from Bath, along with Peter and Veze, who were our researchers at the University of Edinburgh. This project specifically looked at provision of distributed grid resilience using EVs during extreme weather events. You can find more about it here. Alongside this, we're also looking at virtual power plants within the university using AI, and how to operate virtual power plants for resilience, but also decarbonization at the same time. If you find yourself interested in responsive and resilient energy systems, I also want to highlight that we're hosting the Risk and Resilience Day on the 19th of March in Edinburgh. This event is co-organized and also sponsored by the EPSRC Supergen Energy Networks Hub. So you're very welcome to find out more. And if you would like to talk more about it, also please let me know. And lastly, most of the plots and results that I presented in this presentation come from our published work in International Journal of Electrical and Power Energy Systems. So if you're interested in weather-informed optimal scheduling of electric vehicles, and how do we counteract and mitigate some of the negative impacts of storms on energy systems, I recommend that you have this as further study. On that note, I think I'll end my presentation there. Thank you very much.
Yeah, thank you very much indeed, Desen. It's really good to see the sort of the difference in kind of, these future things that, maybe 15, 20 years ago, we weren't even thinking about for the grid, just in terms of, we didn't know where it was going and what was happening. And to see these innovative solutions is really, really interesting. So I'm going to invite all 3 of our speakers back to the stage. They'd like to turn their cameras on. We have had some questions come in, so I can start with some of those. Got all 3 back. Perfect. Thank you very much. So let's start here. So the first one, I think this is probably aimed more towards you, Hazel. Are you able to summarise last winter's seasonal forecast and comment on the performance of the various weather centres? It sounds like it's someone who wants to know which one to listen to this year.
Well, I would always look across I would always look across the different models to show the uncertainty. And if they're agreeing, then there's obviously strong drivers for the forecast. If they're disagreeing, then there's a lot of uncertainty. I'll just share my screen quickly. So these are internal. Hopefully you can see this. So this was a quick, hold on, let me just move the other way. Sorry, James, you're muted there.
It's all right, you can get rid of my face. Nobody needs to see that.
Yeah, if I close that, I don't know if I'm going to disappear. You're going to disappear. That's my slight nervousness. I'll move you down there. this shows the forecast. Let me just make it bigger again. This shows the forecast for, oh, it's not the one I want to show, sorry. Hold on, I'm just going to move you across there. Oh yeah, sorry, no, it's the forecast from November for December, January, February, 2024. So that, and this shows, this is the Met Office forecast, and this was what actually happened. And basically we had a large high pressure, if we can remember, if by the looks of it, we had, I can't quite remember. We had a large high pressure, which is your red anomaly. And the Met Office forecast was this one. So we didn't quite, it's broadly okay, such that you have low pressure over the very high latitudes and then higher pressure further south. But the specifics over the UK are not quite right. Obviously, we had high pressure centered over quite a lot of the UK, whereas we had it more to the south. If we look at ECMWS forecast, they were going for more of a positive NAO, so even further south shifted high pressure. So that's that comparison. And then but in terms of the actual UK specific forecast, so this is temperature on the left, precipitation in the middle, and wind speed on the right. And this are the observations from the last 30 years. And then grey crosses are the observations for the last 10 years. This is the mean, the green, and the blue is what actually happened last year. And so we had a warmer than average being here. And these very faint lines, hopefully you can see them, but the very faint lines are those categories. And so we were just into the, but it's very near the border of the category into the, I think these are the 20% categories because you've got 5 of them. But anyway, our forecast, without going to specifics, this was the forecast that we issued. So the mean being, so it's actually that forecast for temperature was very good. This is the spread of the ensemble, but this was the mean. So it was pretty good in terms of temperature. In terms of precip, it was a drier than average winter last year. And our forecast was basically climatology. And then in terms of wind speed, we actually had a slightly windier forecast, and in reality it was near average. But I guess our aim is not to get exactly, is it above or below, but are we in the right category? So in that respect, we're in the right category. This one is not quite in the right bounds, and this one is correct. So a pretty good forecast, I would say. Not perfect. The pressure pattern wasn't perfect, but reasonable. So that is my summary of that. Hopefully that's useful.
No, thank you very much. I think that very much answers that question. I think brilliant. There's a couple of questions, I think, again, aimed towards you here, Hazel, also, but about looking at the NAO and drivers of the NAO. There's a question sort of asking what other factors may be at play, and also one that asks sort of how well the model is able to account for the differences and the different interactions that you see between the jet stream and some of these other drivers.
Sorry, I've lost you temporarily. Sorry, I'm just trying to get you back. Where are you? Where have you gone?
Can you hear me now?
I can hear you, I just can't see you. So I can't see the questions. From memory, because I did have a quick look at the questions, there's a question from Len about saying that the NAO doesn't drive climate directly, but rather other things drive the NAO, which combine to influence the UK, if I remember summarised correctly. Len is correct that the NAO is an index, so it's a measure between 2 separate points. But it is used to represent the variability. It sort of summarises the variability of winter climate as the first empirical orthogonal function. But however, Len is correct that it is the large-scale drivers, for example, tropical precipitation and variability in the stratosphere, which influence the North Atlantic Oscillation and also the weather in the UK. I saw that Edward had a question about other drivers. So one of the things, we give a forecast at the end of November, we give a forecast for December on average, and then December, January, February. And in the December forecast, there was discussion about the Madden-Julian oscillation and what it was doing, because it basically was in a phase 7, 6, and 7 towards the end of November, which typically would give you higher than average pressure over the UK in the following sort of 10-day, 2-week period. But obviously we're now into the 10th of December, so that period has gone, so I didn't really talk about the MJO, but that can also influence our climate. He also talked about solar variability and the fact that we're near a maximum, and that, yes, there has been work showing that can influence, drive a more positive North Atlantic oscillation in late winter, so sort of wetter, windier conditions. I guess the question is that the models have all these processes in them and combines the interactions of those different processes, and the output as such is the combined process. So we assess the skill of both the UK forecasts, but also of those different processes. And for example, the stratospheric polar vortex, that sort of a combined influence of different processes. And so, yes, we do assess the model on all these different things, and it's has a variety of different skill levels on different processes.
Excellent, thank you. That's answered that one. There's a question here for Desen. What is the impact of EV owners' ability to use their vehicles if they're being used to support the grid? And I guess the question, paraphrase, is what is the public pushback on that? Is there likely that if this is brought in, would this be something the public wouldn't want because they wouldn't be able to potentially use their vehicles?
Yeah, I think that's a really interesting question. We should highlight that an electric vehicle's primary job is being a vehicle and getting people from point A to B. So we're only looking to use EVs as backup if the vehicles are connected and idle. And in the modeling work that we've done, we've also made sure that we always leave the EVs after responding to an event and helping the grid out. The remaining state of charge you have in your batteries will still allow you to do some traveling. So it's not that we would completely take over and use everything up and leave you with zero state of charge to in a state where you won't be able to use your EV. So we don't have any concrete data on what would be EV owners' uptake on this. So what we've done in our modeling work is that we tried out different penetrations of uptake, and we've seen that essentially as long as more than 50% is involved, we're seeing positive effect. So we can use that to hopefully encourage EV owners to take part in vehicle to grid services, but there has been very limited trials, so it's hard to say whether they would push back or not. There's also always the option to override what we try to do. Yeah. So I would say, I think what is the impact on EV owners' ability? Yeah. So yeah, I think that's that. There's also more analysis in our paper if anybody would like to look into that.
Brilliant, thank you. And just as a question, is this something that if it was to be potentially brought out in the near future, would this, would there be kind of almost like a payback scheme in terms of, the next charge is free for owners if they sign up to allow their EV to be used like this, or some way of using it in that sense, so that there is an incentive for EV owners to allow this? So.
Exactly, James. So either like what you said, but also if we were to aggregate all of these different EVs, let's say you're only willing to give up 10% of your total battery capacity, another person wants to give up 50, we could aggregate all of those, present it as a big battery to the grid, and then participate in balancing services and get paid. And then we could distribute those benefits to the users to compensate them for the flexibility they offer to the system when the system was in need. And in some cases, this is very critical to keep the heating and the light on. And in other cases, it's just about having better power quality and more resilience. So depending on how extreme that case is, the higher the incentive would be to participate in the services.
Ah, sounds like a fair compromise then.
Yeah.
I've got a question for Lewis. Mr. Talk. So really interesting to hear that kind of, obviously there's a lot of things going on in terms of protecting these kind of transmission assets, so your substations, your pylons, things like that. Obviously, with climate change happening and us having more flooding and more extreme temperatures, both summer, in particular in the summer, are you finding that there's more or less faults in terms of who's winning the race here? Is climate change meaning that we're having more faults and more problems because things are changing faster, or is National Grid kind of being able to keep up and kind of the resilience they're building into the system is winning out?
I think it's a great question, James. So I guess what I would say, probably a bit political answer, but I'd say it's changing as opposed to one winning. So I guess a really good example of that would be kind of our biggest threat has always been kind of flooding, I would say, in terms of long-term risk to our network. And we saw, I think back in 2007, the PIT review, that various actions came out of that to kind of put flood defense systems in around our sites and to protect them. But now, I guess what we're seeing is changing threats. So wildfires have largely not troubled us in terms of our network, and to this date, we've not seen major disturbances to our network. But we're well aware that over the next kind of 50 years, we think that we are going to start to experience many more. And the nature of them is our network is very vulnerable, I guess, to those kind of threats. So I would say it's changing, but we are kind of rapidly trying to kind of innovate in our situational awareness of how we get ahead of the curve on that front.
Oh, perfect. Thank you very much. If you have any other questions, participants, please do write them in the Q&A box. One, I think, for all three of you that I've got here, and it'd be interesting to hear the difference between those working kind of more weather, those working more in the industry and sector. Obviously, we're seeing sort of these. I think you used the extremes and unprecedented records, whether that be stronger winds, heavier rainfalls. I guess the question is, are we seeing? We're obviously seeing a lot of these because of climate change, but are they things that within your sort of sector that you sort of foresee new challenges coming because of them? And I think you possibly touched on that a bit there, Lewis. I don't know whether you want to start with this one, but these kind of, they're not just things, the same thing but slightly worse. But are there sort of new things coming from it that are as I kind of say, maybe sort of 30, 40 years ago, we weren't even thinking about experiencing?
Yeah, I can go first if you like, Jen. So I definitely think in our sector, we're seeing a period of rapid growth, rapid investment in our network. And in some cases, that's replacing older technology with modern technology. And that in itself comes with challenges. So one thing we've observed is kind of replacement of mechanical-based relays and equipment with what are effectively digital computers. And those digital computers are much more susceptible to temperature extremes than a mechanical relay. So even with technological advances, we still see differing kind of susceptibilities to different climate effects. So I think in one regard, there's kind of technical standards and specifications, but it is that for us, that situational awareness of the change.
And I guess, Hazel, from your point of view, in terms of these unprecedented events, are these weather events that we're seeing just the same events and the same kind of dynamics behind them, but worse, or are we seeing new and different kind of events that we are unparalleled to anything we've seen observed wise before?
So there's a whole body of work. It's called the unseen analysis, which is exploring natural variability in the current climate. So obviously we have a limited record, and that record is changing through time. So you have a limited estimate. So you're trying to estimate the risk of extremes. So for example, perfectly timed. Julie and Kay produced a paper that was all exploring 40 degrees temperatures. So obviously summer extreme temperatures and daily extremes. So obviously with warming, that is what we're expecting. There's a lot of uncertainty about circulation changes into the future. So for example, if we're focusing on the wind sector and wind power availability, future projections are quite uncertain and it's not quite clear. But things we are more certain about are extremes of temperature. So warm extremes, increasing the likelihood of warm extremes, and also increasing the likelihood of rainfall extremes. So with a warmer climate, you can hold more water, and therefore then your rain extremes, for example, the summer is predicted to be more extreme thunderstorms or more rainfall associated with those thunderstorms. So it's not clear cut that every extreme is changing, but certain ones we've got good evidence for.
And I guess you're talking there about sort of, wind generation and kind of, wind time, and that's your sort of specialty. Obviously, sort of, EVs haven't necessarily been around for 30, 40 years, so having that kind of expectation is maybe different. But even just within the short time period, are there things you're seeing which are, surprising and kind of, unlikely to be either seen again or haven't been seen before that, are really, requiring those smart and technological solutions?
So I would say the big pressing issue, maybe going back to kind of the twofold challenge that I talked about in the beginning, is that we're just seeing more kind of that more and new different types of loads. So electric vehicles are one of them, but also we're talking about heat pumps and electrification of different types of energy demand that we had. So while all of this poses a risk, if we were able to use all these, as you mentioned, digital technologies and optimization and things that we wouldn't consider using on these user-owned or small assets on the network, we could coordinate them, package them up as a big bundle of flexibility that can help to reduce demand or increase generation in response to extreme weather or in response to weather-informed scheduling. So weather-informed scheduling also hasn't been a hot topic in energy systems historically, but with the change of the type of storms that people have been experiencing, and especially outages, weather-related outages, and this being more in the news and higher, I think, awareness about it has resulted in this new outlook in energy research, I should say, that's how can we use new and upcoming demand like EVs to counteract different types of risks and increase resilience. On that note, it's probably a good way to plug now that we'll be talking more about risk and resilience in energy systems on the risk day that will take place in Edinburgh. So if anyone wants to talk more about that, it will be just come and join us in Edinburgh. James also will be there.
I am going, yes. I will say Edinburgh is a lovely place if you are, trying to get a few days away. So unless there's any more questions come through on the Q&A, I'll kind of leave with one last question then. So this being obviously the winter seasonal forecasting event, I just kind of want to get your views on, especially for Lewis and Desen, having just heard, what the forecast is. How do you think that's going to affect particularly for sort of Lewis, the operations for what you'll be planning for the next sort of 3 months? For Desen, obviously, how that kind of, whether that gives you any opportunities for any of your future research to potentially do some more case studies. And I guess for you, Hazel, how that's going to, how you feel that, that's going to sit with the rest of the kind of winters that we've had, and whether you feel this is maybe, a potential winter where we might have sort of, some nice, as I said sort of earlier, sort of normal weather, and whether, or whether you think there's going to be some major sort of, talking points. So Lewis, if we start with you.
Yeah, I can jump it. So I guess, hopefully reassuringly, we've kind of completed all of what we call our pre-winter checks by this time in the year. So those are kind of additional health checks that we would carry out on our assets, particularly those that we think are vulnerable or at increased risk. So I think in terms of the forecast, how do we go forward now? We're kind of in the sort of real-time and short-term forecast monitoring. So we would be assessing those forecasts prior to taking any more outages on our network through the winter months, or assessing if we send people out into site during the day for fault rectification, what is the threat to them at that point in time. So I think from a network operations perspective now, we're very much into the kind of, for winter, the short and real-time forecast data that we receive, and using that for decision making.
So it's the kind of, you're now into the reactive rather than preactive.
Correct.
Yeah.
Correct.
No. Thank you. Desen?
Just building on what Lewis has said, essentially I guess from a research point of view, that all of this data, rather than, because we're not operating in real time, it gives us more case studies and trying to figure out different ways we can react, then that hopefully finds its way to operation in real life. One more thing maybe to mention, or another perspective to bring, is that we see a high correlation between flexibility of the users, and we try to forecast that as well alongside using weather forecasts. And maybe there it's also worth mentioning kind of that not every household is able to offer the same flexibility. So I mentioned EVs today. You're going to have only certain parts of the social demographic people, spectrum that will be able to afford EVs and provide this kind of response, whereas these weather events are actually disproportionately affecting vulnerable populations and more critical load maybe. So we'll be thinking hard about, we'll use this weather forecast for future case studies, also thinking hard about how can we find a fairer way to distribute the benefits from flexibility.
Perfect, thank you very much. And then Hazel, your final thoughts on the winter to come.
Well, I can't really give you more specifics than we have already, but it's just worth saying that obviously we give month ahead forecasts and also short-term forecasts that obviously Lewis is very familiar with. So those, in terms of extreme particular events, then they're the types of forecasts that you would use. But I think it's worth just pointing out that we're actually doing more work with NESO, the National Energy System Operator, and DESNZ, and they're using our seasonal forecast now to forecast gas and electricity demand on the monthly and seasonal, well, mainly seasonal timescale. So just to say that the area is evolving such that we're now trying to use those forecasts, the actual numbers, into the models for forecasting demand and wind power. So that is work that's sort of ongoing, and NESO exploring how they can do that. Obviously, their responsibility is to make sure there's sufficient supply in terms of balancing supply and demand. So understanding what the forecast means for them in terms of energy supply and demand and energy security is key. And so we're hoping that these forecasts can now be used more operationally for those activities.
Sounds like foreshadowing for a speaker for next year's event.
Good plan.
Well, it just leaves me then to thank again our three speakers, to Hazel, Lewis and Desen. Thank you very much indeed. Everyone else, thank you very much for joining and for listening in. I hope you found that it's sort of interesting and useful. A reminder that if you do want to sign up to join the Royal Met Society, or even if you just want to sign up to the newsletter or our energy mailing list, please do. You can find that on the website armex.org.uk. I think that's all from us. As I say, thank you very much for joining, and thank you again to our speakers. Thank you.
Thank you. Bye-bye.
Thank you.
Thank you, James, for organizing.